and you can sort of intuitively plug in some values and figure this out. So, or let's say your prediction for, actually we only really in this case, let's say your prediction for 4 was 1. Your model is sure that it is a 1. Then your true class probability, by the way, this would be 0 for all the other indexes I, and let's, our model has predicted 1, so log 1 is 0, which means our net loss becomes 0. So our perfect prediction yields 0 loss. But let's say our model was unsure and it said the probability was like point 1, or that it's a 4, which is a really, really bad guess. We want it to be more sure, like a point 8, point 9, ideally a 1. So if it does this really, really bad guess, we punish it, not really punish it, but we say the loss is really, really high, because let's say log point 1, it's a massive negative number. That's why we add the negative, we get a really, really high loss. So that's intuitively how cross entropy loss works for multiple classes. Okay, is the YouTube back yet? Atreya?
Yes, the
Yeah, I
YouTube is,
think it is.
yeah, it's just up right now. Yeah, I think
Okay,
people are
cool.
slowly, yeah,
We'll just give them a
it's up,
minute or two.
it's up right now. So I think you can continue.
Okay, so then we'll continue. Uh, Hi guys, welcome back. Sorry for that interruption. Where we just defined our model and we set it to the device that we're using, and we define a criterion or cost function as nn dot cross entropy loss. We don't really need to get into the details of this. Uh, we this is essentially like any other cost function. It's just a measure of how badly your model is doing. So if your loss is really, really high, your model is doing really badly, and if your loss is low, your model is doing really well. We'll have a look at what nn dot cross entropy loss is. This is sort of instructive again to using documentation. Look up nn dot cross entropy loss. Go to the PyTorch documentation, and you see that what this expects is this is a criterion computes the cross entropy loss. It's useful in training classification problems with C classes. The input that it expects is supposed to contain the unnormalized logits for each class, which is basically it doesn't want us to normalize our C class input. So let's say our probabilities here were 0.2, 0.3, 3.4, whatever. That's not normalized to be a proper probability distribution. It doesn't expect it. In fact, it incorporates the softmax part itself. So if any of you had the doubt that why we are not doing softmax on our last layer, because PyTorch just takes care of that for me with this loss function only. And then the target that it expects, obviously for a loss function, you need the input data, which you gave it. And to calculate the loss, you also need what the targets were or what the right answers were. And there it just expects the class indice, which is the right answer. It knows that for most multi-class classification problems, everything else it has to set to 0, just has to put 1 next to the correct class. And in this case, very useful, the class number is the actual number itself that we want also, because the index starts at 0. So we just have to put in the right answer. You just have to put in one class index. Of course, it also accepts the probability distribution, but we won't be getting to that. So you can read this on your own time and like try to understand the math as well. It's not too bad. But essentially, this is how you use PyTorch documentation. Nobody remembers what every single function is. Nobody remembers what it does. Nobody remembers what all the inputs that it requires are and how it behaves. And so you can just always look it up and then intuitively understand it yourself. Or if you're looking at someone else's implementation and you don't understand something, you can always look it up and then figure it out from here. And when you get to a later stage, although this is not particularly helpful now, you can also look at the source code because PyTorch is open source. So you can see how this was actually implemented. Anyway, we'll go back to what we were doing. We select an optimizer. I've already spoken about this. In this case, we set the optimizer as optim.atom. Optim from torch.optim is what we imported as optim. So we set our optimizer to Adam. Here we Adam and requires the inputs model dot parameter, and it also requires you to set the learning rate, which we did to be 0.001. And so now before we actually train, we just want to make sure our model is working properly. So we do batch index data targets in enumerate train loader. This is very daunting, and it is in fact lucky for you is very standard. Like you don't have to understand the real working of this. This is a sort of standard way to use data loader and iterate through the data. I'll quickly explain it to you. Batch index. So this is essentially which batch of the epoch you are talking about. So the first batch is zero. That's how it works. So the batch index. And then we noticed that our training data was a tuple containing two columns, the data and the targets. So that's what we're going to denote the first column of that tuple as data and everything in the second column as targets. This will be very useful later. And then we do in enumerate train loader. This essentially tells it to go through the use train loader and go through the training data in batches of 64. Now, if batch index greater than 935, before we get to this, some of you might have had the doubt. Okay, we set the batch size to be 64, but we have 60,000 training data points. So surely, like 60,000 is not divisible by 64, and it should come up with some sort of problem, right? There's an error here. I can't have all the batches of the same size, and you're right. In fact, in this case, there's I think about 937 or something batches. Essentially, what this line does, you can figure out this very basic math yourself. Is we only want to print the last two batches to show you that the last batch doesn't have 64, and this is not something you need to worry about. By the way, we could have had a separate case to account for the fact that it might be not perfectly divisible. But here you just don't have to care. You can set whatever batch size you want. You can set the weirdest prime number on the planet, and it'll still work. So this basically, because I don't want to be printing all the 900 batches ka data, I just want to do the last two. So I'm setting data to device, targets to device, which is basically the tensor that this was and the tensor that this was, which was if you go back to the training data, you'll see that it was the image and then the number corresponding to that image. We set both of them to device, standard practice. And now we do what I told you about earlier is that we'll reshape it to be 784, so we can properly put it into our model. So if you remember correctly, and I just went over this, the original shape is 1,28,28 for one particular sample of the training data. There's 60,000 such samples, and we're iterating in batches of 64. So originally, this data is one entire batch cut, or the tensor corresponding to one entire batch. So 64, 28, 28. That's the original shape, because there's 64 columns of this 1, 28, 20. There's 64 rows of this 1, 28, 28 shaped tensor. And so when we reshape this -1, as I told you earlier, it just compresses the second half of whatever it was. So it takes the 64, 28, 28 and reshapes this tensor without losing any data to be 64, 784. So first things first, we'll print the data. We'll print our targets, and we'll print the shape of the input data, and we'll print the shape of the target data as expected. 64, 784 was our data after we reshape it. So we've properly done that. Targets was essentially what targets we have, which is this. So we have 64, shape of targets is 64 as expected. It's just a array of 64 numbers. So the first one corresponds to a 3, 4. These are what each image corresponds to. Then we do scores, which is we put all our data of the model. We put essentially the data, the 64, 784 tensor, through our model, and our predictions is what we define as scores. So we put in the 64, 784 tensor here, and our predictions is what we'll get out of it. We just put it through our model. What our predictions is what we define scores as, and we print scores and we print the shape. Now this is where we go into our second Slido quiz. I want you to think about what the shape will be of our predictions. we're putting in 64 batch size. So we're inputting 64, 784, and this is what our model architecture looks like. You should be well aware, like familiar with it by now. It has 10 output classes. So what will our output predictions look like? We'll quickly go to Slido, and we'll go back to the quiz. Again, guys, you can join. I'll wait another couple of seconds. If any of you have not joined or would like to join now, you can scan the QR code here. Yeah, I'm seeing a couple of you joining. Anyway, I'll get to the question, so you guys can join then as well. This is the question we already looked at, and so this is the next question, which is what should be the shape of our predictions tensor that we named scores. Your options are 10, 64, 50, 10, 64, 10, 50, 64. You might notice some repeating numbers, like they have some significance. Obviously, you should know, like, have some idea of where we use these numbers throughout our model, and then should be able to work out the right answer. Essentially, what I'm asking is, our model, it outputs something, right? When I give it these 64 samples, what is that tensor? What is useful for us in our output? We also use this to compute cross entropy loss that I spoke about earlier. So what do we require for cross entropy loss? This is one way of looking at it as well, right? For the inputs to cross entropy loss was one particular thing, and then the output was just the right answers. Like the other input was just the right answers. That's the targets. So what is that model predicting? What are the shapes that it's predicting is what you want to find out. Okay, you guys don't have to like worry too much about it. You can just like taking your best guess. I think you just intuitively also you should be able to guess which one might be correct or like have some particular leaning. I'll leave it on for a couple of more seconds. So get your answers in. Okay, we'll move to the answer, which I'm glad a majority of you have got that right. And in fact, the second most voted answer is just an inverse of the first one. So that's kind of a trick to throw you guys off. But yeah, I'm glad most of you have got this right. And the answer is indeed 64, 10. Okay, for the first question, it was bro, and then we have these are the winners. Congratulations, guys! Good stuff. Oh, this is the cumulative fastest time or something. But okay, never mind. So yeah, the shape is indeed 64, 10, and I'll just explain that. Essentially, every output is a 1, 10 tensor, and we have 64 such. If you just ran one image of 1, 74, we used to get 1, 10. So that's a 1 row and 10 column matrix. We get a 1, 10 this thing, and we have 64 of these. So we'll get a 64, 10. So for every image, there'll be a corresponding probability distribution of sorts. Not really exactly a problem, an unnormalized sort of 10 value vector. And then we'll calculate loss. Again, so easy to do with PyTorch. Just loss is equal to criterion scores targets, calculating the loss. As we saw earlier, criterion that we defined as this requires us to put in scores, which is our unnormalized probability distribution, and targets, which is an array of the right answers. So we have done that, and we just print the loss, and this is the output we get. The first, let's go over this. First data is obviously correctly shaped 64, 7, and 84. These are the 64 targets. We notice that there are indeed 64 targets with the shape. And this is what our model is first predicting. So we can see that essentially there are 10 values in one one of these set of braces. You can count them if you like: 1, 2, 3, 4, 5, and 2 rows, so 10. And there are 64 such rows corresponding to each image that it was given. It's giving us a 10 value probability distribution. Notice some of them are negative, whatever. This is just our model's first guess, since it's the first time it's seeing it. And we can see like the correct answer was indeed 64, 10 for the shape. And our loss initially is 2.3062. This doesn't really mean anything. We only want to care that it goes down, but we can see that it's correctly calculating loss. And the last iteration, since 60,000 is not perfectly divisible by 64, indeed doesn't have 64 samples, it just has 32. And it's just the same thing. Again, if you'd like, you can see it. We haven't done any back prop or anything like, okay, for this particular thing, we don't want massive, we don't expect the loss to go down or anything. It'll just be a different loss for this particular batch. So now we get to what we've been building up towards, actually training the model. This is for room for epoch and number of epochs. If you remember, we defined the number of epochs here to be 3. So we'll basically be printing what epoch we're on while we're computing it, and then we're on for batch index. So we'll do another for loop where we basically iterate through each batch. This is essentially identical to what we did here. We iterated through one batch through like one epoch here as well, and we only printed the last 2 batches. So we do exactly the same thing to train our model. Again, we define data targets the same as earlier. This is reshaping same as earlier. Define scores, calculate the loss. And here's when we do the actual learning part. We do the optimization. So again, you have to do nothing, no calculation, nothing. Optimizer.0grad, by the way, when we calculate, we'll have to like continually calculate gradients as we keep training the model, right? This essentially just sets all the gradients to 0 for every batch again, so you don't have any previous influences. This is a pretty standard thing to do. If you don't understand it also, it's fine. In fact, most models will train okay even if you don't add this. Loss.backward. This is all you have to do to backpropagate using PyTorch. You just type in loss.backward, and your entire all computation of gradients, everything is done via this. And optimizer.step. This is all you have to do to implement the ADAM optimizer. You just do optimizer.step. This does your gradient descent, all the updating of weights, biases, everything is done with just this one line, 2-word line of code, which is optimizer.step. And this is actually more complicated than gradient descent, which is ADAM, and this is just the same. You can do it just as easily with optimizer.step. So we train the model, and then we define the check accuracy method. This is obviously the last bit of any training any model, which is where we check how well our model is performing. So we define the method. We define its parameters to be loader and model. Loader, so we can test how well our model is doing on the training data and how well it's doing on the testing data. So we can put in the train loader or the test loader here. Our model, what model we want to be testing said accuracy with. And so we define the variables num correct and num sample. So basically number of samples which our model got correct. So it predicted like correctly for, let's say the image was a 6 and the model predicted 6, then we would increase this by 1. Number of samples is total number of samples it saw. We already know this, that for the training data it's 60,000 and for the testing data it's 10,000. Modern lot eval. This is sort of important, not in this case, but in general, what it does is it sets our model to evaluation mode. It tells PyTorch or whatever, it tells that when the accuracy check or method is called, and model gets set to evaluation mode, and no gradients will be computed, no weights will be updated, none of that is going to be done. We are just evaluating the model. This is important because while we are evaluating it, especially on the testing data, we don't want it to have we don't want to update any weights, biases, nothing. We don't want it to affect the training. We don't, because it is going to go through an epoch or whatever. So we just tell it that we're setting the model in evaluation mode, and then we do with torch.nograd. So again, we just reiterating the fact that we won't be computing any gradients, nothing. For XY in loader, this is essentially what you did earlier when you ran through the enumerate data loader or whatever. XY is here your what your data and targets were. So X is your image tensor, Y is your targets tensor instead of naming them data and targets. Again, we set them to device as we did earlier. We reshape X, we reshape the data to be your 784 compatible one. As usual, we input data into the model and we get predictions, which we call scores. And now we define our more formally what our predictions are, because what scores is we saw earlier is a 64 comma 10 when we have batch size 64 comma 10 this thing tensor, and basically it has the non-normalized probability distribution of each of these values, but that's not really a prediction. I still have to see which one is the highest, and that's my real prediction. That's what this line of code is doing. It's just taking the max of uh, of the first dimension. I mean the second dimension indexing in programming you should be aware of. And if let's say your prediction was equal to y, which is your target, remember y was just the number, the right answer. So if your prediction equals the right answer, then you increase number of correct, and you increase number of samples regardless. This essentially just adds all the size of the predictions, how many ever your batch size essentially. Note that right in the beginning when we loaded the data, here we set the batch size of the test to be twice. So everywhere that we have just discussed at 64, it's actually 128, because when we're running the testing data through the loader, we don't really care to run it in smaller batches for improved training, because we're not training it right now, we're testing it. So we do that, then we just print what our results are. Essentially, this is a fancy way of saying how many we got right out of the total number of samples that saw, and its percentage accuracy. Model.train sets the model back in training mode. So we set model.eval, we set the model to evaluation mode, and we told it no more gradients calculation, no weight updation, none of that is going to happen now. We set it back to training. Now, in this case, it doesn't really matter, because strictly speaking, we are not training the model anymore. We already finished training the model here. We did 3 epochs. But let's say we were to incorporate like checking accuracy after each epoch. We just added the define accuracy check model here, and we checked accuracy after each epoch. Then we would see that after each epoch, when we set the model to evaluation, we should set it back to training, right? Because it's going to do another epoch of training. So in those cases, it's very important. In fact, if we have time towards the end, which I don't think we'll be having, but like if we do, we have a implementation of that as well. We can look at that just to see how good the model's accuracy is after each epoch. And then we just call the check accuracy method with the training data and the testing data. And we find that our model got 57,634 out of the 60,000 ones that it trained on with a 96% accuracy. This is impressive, but this is the data it trained on. This it should nail anyway. But we see that it also has a really high testing accuracy of 95%. So it got 9,553 of the testing data points, right, out of 10,000. So of the 10,000 images, such kind of images that it saw, in like 95% of the time, it was able to correctly identify this digit. And I think that's remarkable that we were able to do that with this little code. We essentially taught the model, or like had the model behave like a baby with a 95% accuracy. If I give it a number like this, if I give it an image like this, it tells me what number that is, which is kind of insane to think about. And why, again, we're going to show why PyTorch is the hero. This entire thing took like, let's count the cells. 1, 2, we don't really need to do this as part of the model. So 1, 2, 3, 4, 5, 6, 7, and the check accuracy 8. So in like 7 or 8 cells, and each of these cells have like a fairly little amount of code. They're mostly just a couple of lines in each of them. We were able to build a model which with 95% accuracy can recognize digits. I think that's really cool, and that's something you can do with PyTorch. And just in case you forgot what Atreya made you look at, This is the same thing hard coded with NumPy, and you should hopefully be able to appreciate this part is the same, but you should be able to appreciate this is already looking bad. How good PyTorch is and how much time it saves you. This is all of this, by the way, like taken care of in optimizer.step or just two words. All of this is done, and the best part of it all is with all this effort, this particular network has a 8.91% accuracy because it took this much effort for you to hard code it, and the optimizer used was gradient descent because hard to optimize Adam using NumPy and some other problems which PyTorch just automatically fixes, like with normalization, this, that, etc. And so we only managed to actually train this on, I think, one epoch or something. The accuracy is just 8.91% as compared to so much less effort and a 95% accuracy. This whole thing can be run in under like probably 2 minutes, and you have a model that with a 96% accuracy will tell you the right answers. So I think we're more or less done for today. Formally, we can close the session. This is the attendance code once again. I will quickly go through the doubts, and if like it's done. If you guys have done your attendance, you guys are free to leave. This is the end of the session. But if you're interested, you can stick around. I think I have I'll do the one thing I promised I would do is and show you the accuracy checking per epoch if we have time for that. But until then, you guys can scan your attendance. I'll leave it on for quite some time. If any of you have missed this, get your scanning and get your attendance. Okay, I will just quickly look at the Slido doubts. Okay, I saw this by recent. Yeah, okay. When should we use cross entropy and when mean square error? This is actually a very good question, and it's quite interesting. It's not. It depends mostly from, like I say, from case to case. In fact, these loss functions were developed with time, depending on the type of machine learning that we were trying to do. So in with cross entropy is a very good way, as I explained mathematically, especially when the YouTube was down, is a very good way for multi-class classification to gauge how well your model is predicting the probabilities for like multiple classes. Mean squared error is usually used when you want your model to predict a single value, or it's sort of like linear or polynomial sort of function, and we looked at like linear regression and polynomial regression in previous sessions. But that's usually when we use mean squared error. Of course, you can test out a lot of new loss functions and in different models, and it's so easy to do in PyTorch, right? You just go up here, you change what are the criterion, and you retrain the model, see how your accuracies are affected, etc. So then you can just see whichever one's giving you the best accuracy. Also, you should have some logical intuition why cross entropy is good for classification and mean squared error is good for prediction tasks. What's an epoch? An epoch is when your model sees all the data for like all of the data, all the training data once. Basically, earlier when you give it all the training data at once, that's just one iteration is an epoch. But here I'm sending it in batches of 64. So your one epoch is completed when it sees all the batches once. Okay, okay. Working on facial recognition system. Okay, good to know. For our classes, some pro using face detection depends upon the light conditions. Can I suggest solutions to improve? I think this is not not strictly speaking relevant. But this is cool if you guys are working on this. I think even with the QR code, we are struggling a little bit. So I'm not sure how the facial recognition system will fare, but we're open to try. Lighting and all, I think the more you train it, the lighting conditions, especially if you train it with bad lighting conditions, etc. In your training data set, then it will learn to do better in lower lighting conditions. So that's
So
something you
yeah,
can
you,
try.
you you'll have a session later on convolutional neural networks where you'll be going a bit into detail about all of this. So stay tuned for that. I think that might help clear up some confusions that you might have.
Yeah, and in general, let's say your classifier was trained. You were doing a classifier that was detecting, essentially told you whether an image is a cat or not a cat. And all of, actually, I'm not even going to get into that. Our entire model is trained on such images, right? Handwritten images, black and white, of 504, whatever numbers. Let's say now I feed the model an actual photograph of someone writing with pen, with like on a red background, writes with green pen or something. That's going to completely throw off my model, because all it has seen 60,000 such images of training. That's all it is trained to do really, really well on. Now, if I give it something new or something slightly different, in this case, let's say most of your images of your training were in really good lighting setups. Now, if you give it something with a bad lighting setup, it's likely to screw up. So if you just train it on those as well, it'll do a lot better. And we can sort of like take care of this by diversifying our training sample or whatever. But yeah, that's something that we have to keep in mind. It's also like you can see the biological mirroring here as well. If let's say as a child you were only exposed to writing in black and white, and suddenly one day someone, like, okay, you would probably as a kid learn pretty quickly in green and red, and even your network with, if you give it like that. But suddenly if you give it green and red images, it might have problem processing what it is or what it means, or it's actually the same as numbers only. It might think that you might actually think that has a completely different connotation to it, like let's say time or something is denoted in red and green images. I don't know. I think we last out we have, do we get a recording of the part where the YouTube was down? We'll work on this. Essentially, what we did is just looked at the mathematical implication of cross entropy loss. So I'll probably can, if you have a recording, we'll just share that. If not, we'll just you can look up a YouTube video, or we'll share a YouTube video that explains cross entropy loss. It's not that important for the general session. MSc versus MAE. This is again like a discussion for a later time, but these are both loss functions, by the way, mean squared error and mean absolute error. Generally, what we know is mean square error. Essentially, mean absolute error makes you like compute. You do it everything with a mod, right? And we know that for our backprop and for our model, we require to calculate derivatives and stuff, which is kind of a pain with absolute error. When you take a mod, it's kind of painful already to start going into the derivative and stuff. So generally, we just don't want to deal with that and use the square, because polynomials are very easy to differentiate as opposed to this. There's also some like finer details and other problems that come with your roots and stuff that we'll look at later, and how many minimas your loss function has. But that's not like strictly speaking relevant. A lot of use cases MAE performs just as well, and you can test it out in any case that you're using MSc, just to see how your model is performing, whether it does better or worse. Okay, I'm just seeing if I missed a question. No, I think we're good. I will just once more show the attendance QR code, and I think we can wrap for the day. Maybe I will just quickly show you the define accuracy placed inside the training loop. Yeah, okay, like really sorry guys, we didn't mean to overshoot. We had the trouble with the attendance link, and then the YouTube stream stopped working, which has never happened before. But yeah, we really didn't want to overshoot, but I think we did a pretty decent job, especially because like we formally ended the session a little while ago. So we tried not to overshoot as much as possible. As for this accuracy checking implementation, essentially what we did is, if you remember the code, this is all okay. Before we trained the model, we moved our our accuracy checker by definition to be before we did our mini test, just to see how bad our accuracy was the first time. And we put this def accuracy method essentially in our training loop at every epoch inside the for loop for the epoch. So you will see the indentation as you do in Python. As you do in Python, it prints the training and testing accuracy during every epoch. So we see at the end of the first epoch, our accuracy was training accuracy was 93.2 and testing was 93. And then at the second, it was 95.13, and the testing accuracy was 94.77, and the third epoch, it was 96.08 and 95.57. So you can see that it's slowly improving as you train it more and more. But it's also like the growth here is pretty small, so it's pointless to keep training it. Yeah, I think that's about it. And we can, if you'd like, we can share this notebook with you, but it's very easy for you to do as well. You just, the notebook that I was working on this entire session, this one, you can just move the accuracy check method above the training, and in the training loop you can do what I did and add the accuracy checking in the same for loop as the epoch. Okay, so I think we can wrap up the session. Thanks a lot for joining in, guys. We hope you found it as
Thanks a
exciting
lot.
as we hope.
We hope you found it informative and useful.
Yeah, like you started today with your basic analytics knowledge, and by the end you've managed to basically understand all the basics and build a model of your own that can mimic a human learning or a baby learning, which I think is pretty cool.